disruption, Farmer John has n pastures with n-1 bidirectional pathways. He's going to go through each one of these pathways and remove them. He also has m additional bidirectional pathways. These are only going to be used if one of the original pathways are blocked. So for each one of the original pathways on the farm, we need to find the shortest replacement pathway of the m additional bidirectional pathways that will basically allow the farm to be fully connected again. Let's go look at the algorithm for this question. There are a couple things about this question that tell us what algorithm we should use. The first and most obvious is just that there are n pastures and n-1 pathways. And when we have pathways and pastures, that basically means it's going to be a graph. And since there are n-1 edges, then it's going to be a tree. And that's going to be important for our algorithm. When we have a tree, if we have an edge connecting two nodes, if we get rid of this one edge, then these two are essentially going to be separate subtrees. So with our tree being the nodes, being the pastures, and the edges being the pathways, then we can basically create and realize that removing one edge is going to give us two separate subtrees. Now, when we remove an edge, the question is asking us for the smallest or shortest possible way to basically reconnect them. And since when we remove an edge between a parent and a child, no other edge is going to basically reunite those two subtrees. So we can assume that we have two separate subtrees. There's no way we're going to have, for example, three separate subtrees since we're only removing one edge. What we can do next is we're going to have our two separate subtrees. For example, if we were to move the edge in this example here, then we have this subtree and this subtree. And in order to reconnect them, we can look at our m extra edges, and I've drawn them to be purple here. And for each of these edges, we can classify them into two different categories. They're either going to be within the subtree. For example, this edge here, it connects two nodes that are part of the same subtree, or it's going to connect two nodes part of the different subtrees. So if this node is connected to this node through this edge, since these two are part of two different subtrees, this edge essentially connects them and essentially connects these two subtrees together, giving us our answer. So what we want to find is the shortest possible edge that connects one node from each subtree. If we were to brute force this question, then what we could do is we could basically check every node from each subtree and then check to see if there's an edge connecting between the two subtrees. But in order to speed this up, we're going to use the merge small to large algorithm. And that algorithm basically is going to take two different nodes or a couple nodes, and it's going to merge up in the fastest way possible. And so when we merge two different nodes, what we can do is we can actually keep a set of the different edges of the m additional edges. We can keep a set of the different extra edges that are connecting with this node. So for example, for this node right here, then we're going to have this edge here, but also this edge here. So it's just going to store those two edges. For example, for this node, it's going to be this edge. For this node, it's going to be this edge and this edge, and so on. And when we do that, we can apply merge small to large so that every time we merge two subtrees, what we actually end up doing is we're not going to look at the size of the children. We're going to look at the size of the sets of the extra edges. So if we were to merge these two nodes together, we'd check and merge the set of the number of edges that connect to this, and then the set of the number of edges that connect to this. So merging these two would basically essentially be merging a set with this edge and this edge. And then when we do that, when we merge two nodes together, sometimes their sets are going to have an overlapping edge. For example, when I merge this one and this one, it's going to have this edge. So this node has this edge, and this node also has this edge. And actually, when that happens, we can realize that it means that this edge is in the same subtree. It's not useful. We can basically get rid of it if it's in both this one and this one, because every edge only has 2 endpoints. And if both endpoints are being merged together, then that means this edge is going to be connecting 2 nodes of the same subtree. So since these 2 are merged together, they're going to be part of the same subtree, and this edge essentially is not going to be useful. It's connecting 2 nodes in the same thing. It's not useful. So when we merge them, if an overlapping edge happens, we basically remove it from the set. But if not, then it's only going to give us a set of the edges that are external to our current subtree. So by the time we merge, for example, when we merge all of these together, our set will only have the external edges linking to any other part of this other subtree. And that way, the more we merge, the only edges that we have in our set are going to be external edges. And when we do this, which we're going to do using a DFS, we can also basically keep track of the shortest edge in our set. So for example, again, once we've merged this, we know that the shortest edge is going to be here. So our answer for removing this right here would just be this answer. So I'll explain this more when we get into the code, but basically once we reach a certain node after merging all of its children, whatever is the smallest value, or whatever is the edge with the smallest value in that set, is going to be the answer for the edge with this node and its parent. Since essentially the subtree of any edge, the 2 subtrees are just going to be whatever the child this edge used to connect it's going to be its entire subtree. So it's just going to be its entire subtree and then the rest of the tree. Meaning that once we merge up to this, whatever is the smallest edge is just going to be our answer for the edge that was originally connecting this node to its parent. Let's go look at the code for a better understanding. We're going to start off by reading in our input into the adjacency list. So that's going to be our 2 nodes, and then we're just going to push it back into our adjacency list. After that, we're going to read in our M edges. For each one of these, we're basically going to insert them into our node set. And that's going to be the data structure we talked about earlier. That's basically going to store the value of each M extra edges that is connected to this current node P. So for each one of these, it's going to be inserted in a pair of the value or the weight and then the index of this edge. And that way, since we're inserting the same thing into both, when we end up merging them, if they both show up in the same set, then we can cancel them out since they're stored as the same value. We're going to do our DFS, which is going to do our merge small to large. And while we're doing our DFS, we're also going to get our answer for every individual node. And so once we're done with that, we can output it. So when we have our output, we're going to have the 2 nodes, and then we're going to basically get the top and the bottom, and then we want to basically find the edge that is connected to the node to its parent. So we're going to output the answer of the lower node, so if the parent of SV is equal to FB, meaning if our first value input is on top, then we're going to swap them. Now, in order to actually get that answer, we're just going to do a DFS with a merge small to large. So the code I'm going to paste in here, it has 2 parameters, the node and the parent. We're going to do like a normal DFS, and we're going to loop through all of the children. As long as that child is not the parent, then we're going to assign it its parent value, and then use recursion to DFS. So this DFS is going to return the value of the size of the set, so the size of node set C. And using merge small to large, we're basically just going to see whichever one is a bigger size. And if it's bigger, or if the child set is bigger, then we're just going to swap the 2 sets. Then we're going to loop through the smaller set, and then we're just going to find the number of, or actually loop through and then insert them into the current set. So if node set N contains the value of S, and node set C contains the value of S, then the same edge is in both sets, meaning the edge is internal to this current subtree. And for this question especially, since we don't want any edges that are towards internal trays, so if the edge begins and ends in this current subtree, since we're combining these two sets, we don't need that anymore. So we're just going to erase it. If not, then we're just going to insert it into node set n. Then at the end here, we're just going to check to see if there are any external edges in node set n. And if there are, then it's just going to be the smallest value. Since it's a set, that's going to be sorted. So we're just going to assign answer n to the smallest possible edge. Otherwise, it's -1. Then at the end here, again, we're just going to print out that value. And that's the end of our program.